Hello everyone, you're about to watch the video on Chapter 4, Exponential Modeling. You should have your note paper in front of you, and we're going to go through some review. Some of the stuff you will have seen in Algebra 2, and some of it may be new to some of you. So as we go through, you're going to have some practice problems to do, so hopefully you have your calculator handy, you have a piece of paper, and you have your notes pad in front of you. So let's get started. First, growth and decay. Linear growth occurs when something increases by a fixed amount in each equal time period. Exponential growth, however, is when something increases by a fixed percentage of the previous total. So let me give you a couple of examples. So here's an example of linear growth. So you're starting off with the x and y, so your x's are just 0, 1, 2, 3, 4, 5, 6, 7. The y's are 5, 10, 15, 20, 25, 30, 35, 40. So notice that the difference in each case is 5. So it's increasing by 5 each time. Exponential growth is also interesting, but what we really want is a linear model, not a top model, a linear model. Exponential growth. So see what's happening here, 2, 4, 8, 10, 16, 32, 64, 128. So notice what's happening is it's increasing, it's being multiplied by 2. The difference is not staying the same each time. So that's an example of exponential as opposed to linear growth. The ratio, however, is the same. You're multiplying by 2 each time. Okay, so here's an example of a scatter plot and a least squares regression line that shows the brain weight for 96 species of mammals. So across the x-axis, you can see the body weight in kilograms. So down here. And over here, you have the brain weight in grams. And so you can see you have a great big cluster of animals down here, but you have a few outliers. So, what do the outliers tell us? Well, think about it for a minute. What do the outliers tell us? Well, I noticed that dolphins and humans have large brains, but they're not very heavy. So dolphins and humans are smart. Hippos, however, have a great big body and a very small brain. So hippos are dumb. Oh, he doesn't look happy that I said that. And finally, we have elephants. They have big bodies and also big brains. So elephants are just big. Oh, here he comes. Get out of the way. All right, so let's remove those outliers. So if we take those outliers away, here is that same data plot that we just saw, except now we're able to focus in on the grouping that was down at the bottom. Does that look linear? Well, I don't think so, because you can see that it kind of curves. Follow my arrow here. It curves around in this direction. So this is not a linear model. However, if we were to take the logarithm of the brain weights and the logarithm of the body weights, well then it becomes a linear model. So this allows us then to start talking about least squares regression lines and R values and R squared values and things like that. So what we're doing here is we're transforming the data from a non-linear or curved model into a linear model by taking logarithms. Transforming data. So I talked about transforming, and I mentioned transformations there. Applying a function such as a logarithm or square root to a quantitative variable is called transforming or re-expressing the data. And understanding how simple functions work will help us choose and use transformations to straighten nonlinear patterns. So we have to know how the basics work. So what we're doing here is we are transforming, there's our transformers, we are transforming the data into a linear model from a nonlinear model. So here's an example of this. The number of cell phone subscribers in the United States. 1990 is the starting year, not a lot of subscribers. By 1999, we had a lot more subscribers. Right, you're all familiar with this, so there's someone talking on the phone. So the number of cell phone subscribers in the United States. If we were to graph this, you should hopefully see a very distinct curve. This is not a linear model. This is a curved model. Looking at the ratios, so if I do 24,134 divided by 16,009, I get 1.507. 33,000 divided by 24,000, 1.39. 44,000 divided by 33,000, 1.30. 55,000 divided by 44,000, 1.25. Notice that it's not the same each time. Right? The ratio is getting smaller. If we take the logarithm, so I'm going to take the log of the subscribers, and you can take a log just using the button on your calculator, log 5,283. You get that. Log of 16,000, 24,000, log of 24,000, log of 33,000, and so on and so on and so on. Notice that it becomes, in this part, a fairly linear model. 4.2 to 4.3, 4.3 to 4.5, 4.5 to 4.6, 4.6, 4.7, 4.8, 4.9. It's not perfect, but it's better than it was before. And there's a picture. And you can see that it is much better. It is much more of a straight line than it was before. And we did that by taking the logarithm of the subscribers, so the logarithm of the y values. Okay, so I've been talking a lot about logs. And some of you, hopefully you recognize the word, but you may not remember anything about logs. So let's do some log review. Not these kind of logs. All right, definition of logarithm. Suppose b is greater than 0 and b cannot equal 1. There is a number p such that the log base b of n equals p if and only if p to the b equals n. All right, that is your basic definition of what a log is. That should be in your notes. Let's do an example. So if I wanted to evaluate this, I would set it equal to x, and I would do 3 to the x equals 27. So the square root of 3 to the x equals 27. And I'd want to figure out what x is. Well, the square root of 3 is 3 to the 1/2 to the x has to equal 27 is 3 cubed. So now if the bases are the same, then we get 1/2 x has to equal 3. So x has to equal 6. So my answer then is that this value equals 6. Gotta get those logs in there. Okay, let's do another example. So I have equals something out there. So 6 to the x has to equal 1. Well, 6 to the x has to equal 1 is the same thing as 6 to the 0. So therefore, x equals 0. So therefore, this equals 0. Okay, another example. Equals something. So 9 to the x has to equal 729. 9 to the x has to equal 729 is the same thing as 9 to the third. So therefore, x equals 3. So my answer is 3. Right, and you can ask you to evaluate, so it's the same idea. 3 to the some power has to equal 27. So 3 to the power has to equal 3 to the third, because 27 is 3 to the third. So therefore my answer is x equals 3. And one last example. 7 to the x has to equal 7 squared. So x has to equal 2. All right, your turn. So on your paper, there are 16 practice problems. What I'd like for you to do is press pause, do those 16 problems, do them on your own, and then once you're ready, and you're ready to continue, if you press play, the next slide will have the answers. So go ahead and press pause and do these problems. Alright, if you advance to this slide, you should have already done those problems on your own, hopefully. You did them already. I'm trusting you. Be honest, working together, working through it, doing the work on your own, not just going directly to the answers, because that's not going to help you. So here are the answers. So check your work and see how you did. Now these are all very basic log problems. Okay, so now we're on to the next page of your notes. Log laws to know and love. First, if you have a log of a times b, you can split that up into log a plus log b. All right, this is on your next page of your notes. If you have a log of x to the n, you can bring the power, the n, in front. So it's n times log of x. That's another law. Here's an example. If you have the log of 100 times x, you can split it up. Log of 100 plus log of x. Well, log of 100 is 2. If it doesn't have a base down here, then we assume it's the common log. And the common log is always base 10. So that's why this one was log base 10 of 100. So it's 10 squared has to equal 100. So then this has to equal 2. And then see how I brought the 3 in front. So the 3 comes in front. Log of 100 we just said a minute ago was 2. 3 times 2, your answer is 6. Okay, so let's do a couple of examples, and you can try these on your own and then write the answers down. So we have log base 2 of 8 plus log base 2 of x. This is 3 plus log base 2 of x. Right, so that's the way you would simplify that. Okay, for this one, you would bring the x in front. So I bring that in front. So it would be x log 2 of 8. Log 2 of 8, we just said a minute ago, was 3. So then my answer would become 3x. This is a common log. So if I bring the x in front, I get x log of 1,000. Log of 1,000, remember it's a common log. So that would be 3. 10 to the third power. 10 to the third power makes 1,000. So this would also be 3x. And then the last one, you can split that up. So it becomes a log 10 plus log y. Remember this is a common log, so 10 to the first equals 10. So this would be 1 plus the log of y. And that would be your answer for that one. Okay, so observe the following chart. Why do the values in this chart exhibit an exponential growth? Well, notice this was what we did earlier. 1, 2, 4, 8, 16, 32. They're multiplying by 2 every single time. So each time, we're multiplying by 2. If we fill in the third column and compute the log base 2 of each y value. So if I take the log of 1, the log base 2 of 1, so the log base 2 of 1 equals 0. The log base 2 of 2 equals 1. This is 2, 3, 4, 5, 6, 7, 8, 9. So notice we go from an exponential pattern to a linear problem. Right? This is transformations. So what we call this linearizing, I don't know if this is a real word or not, but I'm going to make it up. Linearizing the data, making it linear. And I don't know if the spelling is right or not, so don't get on to me for all you English, future English teachers out there. I think it's right, but I don't know. Exponential growth model. What is the major difference in an exponential growth model? Let's see, in an exponential growth model, growth depends on a repeated multiplication rather than addition. The model for exponential growth is y equals ab to the x. These problems are characterized by change over time. If a variable grows exponentially, its log will grow linearly. Alright, everybody got that? If you haven't gotten it yet, press pause. I'm going to go on. Alright. That's all I've got. Have a good evening, and I will see you in class tomorrow.